So thank you so much for coming here. Thank you for the opportunity to speak. As I was introduced, my name is Johannes. I'm maintaining Git for Windows. And Git for Windows is actually a little bit of a pun in this title here, the Making Git for Windows, because the first half will be what I originally intended Git for Windows to mean, like Git for people who work on the Windows platform, so who have a Windows computer. But the second half, that's Stolee, he will be talking about Git for Windows, as in the developers who develop Windows, because they are now on Git. So, yeah, I should actually start out by the credits. A couple of people I would like to thank, and one in particular I would like to point out. Johannes 6th is the other Johannes who worked primarily on Git for Windows before it became really officially available. And he basically took all the patches that I had and left unfinished and made them usable. So without him, this wouldn't happen. I wouldn't be working at Microsoft, and we wouldn't have had this really great opportunity now. As to the timeline, a couple things. So most of you probably know in 2005, Git started. From 2005 to 2007, Git did not really work on Windows. You had to install something that's called Cygwin. And Cygwin is basically something that brings you the functionality of Linux to Windows, but it emulates things, so it's slow and it has problems. So that's why I started to work on this whole thing. And the first Git for Windows packaged and compiled so that users would not have to build it all themselves. It was actually done in 2007. So I completely missed that time, but last year we could have totally celebrated the 10 years. So let me first describe a couple of problems for the Windows platform, because many of you probably do not really suspect, except when listening to Ed's talk, that most of the Git development does not actually happen on Windows. It happens on Linux. I actually claimed yesterday on the Git mailing list that all of the core Git reviewers are on Linux and nobody cares about anything else. And somebody came back, no, I'm on a Mac. So that's where we are. Most of the core Git reviewers, so review, as we heard today, is very important, and I totally agree. Review is what makes your code better. Most of them are actually on Linux. So the first challenge to work on Git for Windows is to make things work on Windows, even if they're really optimized for Linux. And a couple of things here I would like to point out, in particular, the scripting environments. So Git is written in Portable C. Everybody knows that, right? Except for the parts that are not written in Portable C. So some are in Unix shell scripting. And Windows users don't know Unix shell scripting, because as the name says, it's on Unix. But now if you want to run an interactive rebase, the interactive rebase is actually implemented as 2 shell scripts. If you run a rebase, it's either interactive, or it's merging, or it's the standard one. In total, there are 4 Unix shell scripts involved. So how do you execute that on Windows? You need a bash, or a Unix shell interpreter. And that's a foreign thing for Windows. For example, if you have a script and you want to mark it as executable, there's no such concept on Windows. You can't mark a script executable. It's not. Exe files, batch files, PowerShell files, they are executable. Everything else is a plain file. So these are the challenges. And of course, this is one component that Git for Windows has to ship, has to bundle in the installer. And there are many, many more. In total, we have something like, I think the last number was 141 different components making up Git for Windows. And Git is only one of them. So basically, maintaining Git for Windows is about 140 times as complicated as maintaining Git. Another really fantastic problem that Windows users have are line endings. So, this comes from the DOS times, and the DOS times come actually from IBM. IBM produced typewriters. So you hacked on your keyboard, and you made a mistake, and you couldn't really fix it. But then next line meant you took that thing, and you moved it all the way there. And it did 2 things. One was it moved all the way there so that you were at the first column again. So that's the carriage return. The carriage is this thing here. You probably don't even know how typewriters look like. But anyway, so the next thing is it also moves that thing forward, so a line feeds, so that you're at the next line. And so that's how line endings look like on Windows. On Unix, they're just the line feed. They implicitly do a carriage returns. Sometimes it actually works. But Linux developers do not care about this. They always have only one line ending and say, yeah, you Windows developers, you care about that. And when there's a problem in the conversion, yeah, right? So this is one of my favorite problems. Then another problem is that everybody on Linux assumes that every absolute path starts with a slash, because that's what it does. There's a unified file system. Even the devices are mapped into that, so they start with /dev. Wonderful. On Windows, it's not that way. And by the way, I often hear that this is POSIX convention, the thing on the left side, but VMS is also POSIX, and VMS paths look totally different. You would run away screaming if you would see them. But Git doesn't handle them. And Git doesn't handle Windows paths very well either. So we have to deal with that somehow in Windows. Also, we have to deal quite often with spaces in file names, because program files itself already has spaces. And Windows 2000 documents and settings had 2 spaces for the price of 1. Wonderful. On Linux, nobody puts space into their file names. Everybody knows better than to do that. But we can't. And also, another really good point here on the slide, that was not my idea, Stolee pointed that out to me. I thought, yeah, everything that you configure is in etc. On Linux, that is the case. On Windows, you usually put that into a registry, and so Git doesn't have a concept of registry, and so we don't do that there. We use a very foreign system when it comes to Windows. And to those of you who listened to Ed's talk, you probably remember the really horrible experience that you have with cloning and checking out a file, and all of a sudden you get this, I can execute all kinds of code. That's only because on Linux, nobody thinks that anything is case insensitive. And on Mac OS and Windows, it is case insensitive. So we still have many problems there. They're not solved. There's still a lot for us to do. There's just more pressing issues and not enough contributors taking care of that. But for example, if you check out a branch, and then later you check out another branch with a different case, then you get that branch again, but not quite. So sometimes it says there's no branch. So it's very entertaining. Lots of us for us to do. Also, the expectation of users is that there's always a graphical user interface that guides you through things. And so the guiding aspect is very important. On the command line, you're greeted with a blinking cursor, and you don't know what to do, right? With a graphical user interface, you at least have a menu that says you can do this, 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 and this. And if you don't know what this is, at least you know there's something you could do, and you probably want to look up what that is because you might want to use it. On the command line, you can't. So if you present a Windows user with a command line, they tell you, OK. So this is how it looks like. That's actually on Windows, because on Windows we emulate the Linux experience in Git for Windows in the Git bash. And this is how it can look, and that's much more intuitive to use. But that's also another challenge on Windows. I briefly mentioned this problem with the scripting environments. This is not only a maintenance problem, because I have to update whenever a new bash version comes out. I have to update Git for Windows, actually. And it's also a problem because of the speed. Unix shell scripts execute at a really excruciatingly slow speed. Just for comparison, in the test suite that Git itself has, the interactive base is tested in one file, and that file runs in about 30 seconds in a Linux VM on my machine. And the same script takes about 10 minutes on Windows. And that's only because it's using this Unix shell scripting. So these are problems. Also, other problems that, yeah, Johannes, please expand thoughts. I should have probably expanded on those. But there are many differences. So on Linux, what you have is this concept of you can mark things as readable, writable, and executable. And you can do that for the user who owns that file, for the group that owns that file, and for everybody else. On Windows, you have a much more complicated thing. You have ACLs, access control lists, where you can specify exactly who can do what with your files. And there's just no mapping. But Linux assumes the Linux semantics. So in Git repositories, you have the, oh, yeah, it's executable or not. On Windows, it doesn't make sense. So yeah, I should probably not even talk about that, because I will only run out of time. This is another thing that's showing you the problem with the POSIX emulation layer that I mentioned earlier. When we execute Unix shell scripts, of course, there's an emulation layer that makes it look almost like we're on Linux, but it's with flaws. And these flaws, they hit users. And the user experience of seeing something like fatal error, sig heap base mismatch detected, this user experience is really crappy, right? So we managed over the years to reduce this, but it's still not gone yet. So there are tons of stuff that we still need to do. Maybe push more for portable C, maybe go for alternatives. So all these are really fantastic problems that we face, in addition to packaging all that complex system with 141 packages. For this latter part, what we use is automation. So for the first 10 years of Git for Windows, almost 10 years of my involvement in Git, I did this as a hobby. Since 2015, I work at Microsoft, and we have this cloud that I now have fantastic access to, and I use this. So for automation, I use Azure. I use the build agents and VSTS. And what we can do there is, for example, take all those patches that we have to make things work on Windows that are not yet in core Git, take all those patches, and whenever something changes in the branches of core Git, we move them all on top of there and test everything whether somebody broke something on Windows. Because, as I said earlier, nobody cares about Windows on the Git mailing list. So when we find breakages and can just paste the error, then the developers say, oh, yeah, probably I should do this and that. And then we can fix things. But that's all automated. Right now, it's broken. I need to fix it. But once I fix it, it works again, and then we don't have to do that manually. So this saves me about 5 hours per day. Another thing is that we also test our patches that we want to contribute to core Git, of course, but they're still stuck in the Git for Windows fork. We test this also on Linux and Mac OS, because we can, because on VSTS we have the build agents, to make sure that we don't introduce something that has the problem in the other direction, where people would say, oh, you don't care about Linux, it doesn't work there. So that's something that we do with all of our patches. And then also, whenever a new Git for Windows version comes out, what we do is hit a build job saying, so this current version that's on master, why don't you make that? And about 1.5 hours later, there are all these artifacts, all the files. I test manually. And after that, I hit another button, and it automatically uploads it to GitHub and to NuGet, and it sends the announcement mail. And all this is automated. So this takes about, just for comparison, to make a release before that automation took me about 2 to 3 days, including manual testing. And now it's often done within half a day. And most of that is just me doing other things while VSTS does all the work for me. So with this, I would like to hand over to Stolee.
Thank you. And thank you, Johannes. Sorry for the slide bugs. If only we were using version control for PowerPoint. Sorry, those were my fault. He had made some changes I forgot to apply. But I'm going to talk about the second half, which is instead of making Git for Windows, we're talking about improving Git and specifically for the Windows operating system developers, but then those benefits are going to get to everybody on all platforms. Last year at Git Merge, our colleague Saeed announced that Microsoft was moving the Windows development team to Git using a new tool called the Git Virtual File System, or GVFS. And then later that year, Brian Harry announced that the entire Windows team had transitioned and that we had said, mission accomplished. All right, we're done. No, we're not done. We just made sure that it was possible and that they can do their work. They're not inhibited, but it could be better. The Windows repo is really big, and I just want to, sometimes people say one number, like how big a checkout is, like it's 3.5 million files, it's 300 gigabytes if you were to have it on your local disk. That's all what GVFS was supposed to do by virtualizing that and not actually taking up that much disk space. But there's lots of other things that make the Windows repository big, and comparing it to what's normally the big repo of Linux, the Linux kernel, the few ones I want to point out is the .git/index file is a very important file. It helps hold your staging area, and it's 260 megabytes in the Windows repo, and that's a huge hindrance to us being able to do fast commands. There's also 48 million objects in the repo. 1.7 million of them are commits. So there's a lot of places where we're an order of magnitude larger than the Linux repo. The only one we're not is how long we've been around. This is only about 1 year of history in active development, while the Linux repo has been around for 13. So that's a lot of activity very fast. So why is this? Why is it getting so big so fast? Well, first off, it started out with a very large work directory, right? We do have 30 years of Windows development that then was just a snapshot of the working directory. But there's a lot of developer interaction every day. There's over 4,000 engineers where this is their job to contribute to this repo. That's their main job. They're located in 3 different locations around the world, but there's also a lot of smaller groups that do other things. There's over 90,000 branches that are actively used by our developers, and they're pushing 3,000 times a day and completing 2,300 pull requests a day. And I'm counting weekends there because time zones and stuff, but that's a lot of activity, lots of movement. So what we want to do is try to make sure that all these developers that are working in this repo do their work as efficiently as possible, and Git should be out of the way. And our #1 benchmark for how well we're doing that is by measuring Git status. Git status is so important because you really can't make a commit safely without using status. You need to know what are you going to be committing. And it tells you where am I in my process. A lot of GUI tools are always calling status. Visual Studio calls it, VS Code, et cetera. So it's something that is very frequently running in the background, even if users aren't directly doing it. So it might slow down their machine if it's too slow. And then it also it's a good benchmark because it touches all of the important data. It touches the working directory. It does file hashing. It's got that .git/index file that we talked about. It's 260 megabytes. And as we discovered, it also touches commit history, and we'll talk a little bit more about that. When we announced GVFS, we said, well, before GVFS, this status would take 10 minutes to complete because it would walk the entire working directory of 3.5 million files, and that it would just be waiting for that. With GVFS, we were able to get it down to a typical 5-second time. That's not good enough for us. We want to get down to less than a second because that way it feels more immediate. Developers aren't just saying, oh, I typed a command, now I'm waiting. Oh, now it's done. OK. So we want to get there, and we're trying to find out how, and we're working in multiple directions on that. But this 5 seconds is also only a typical command. We were seeing that some status calls were really slow. The nice thing about having the Windows developers running Git is that they're a very captive audience. They have to use the tool to do their job. And because the Windows development group really cares about whether or not tools are getting in the way of their developers being efficient, they have a telemetry stream that tells us, hey, here's how long it's taking people to run status, and here are the different percentiles. And we're seeing a very long tail where, yeah, the 80th percentile is around 5 seconds. That's great. But you look at the 95th percentile or the 99th percentile, and you start getting scared. So we're trying to figure out what's driving that long tail. And it took us a while to find a repro. So here I have the command line for a status from my local box, my dev box, about where I said, hey, this took over 20 seconds. Let's find out why. And the first thing that struck me was actually there's nothing in the staging area, there's nothing untracked, there's nothing that I changed. That's usually what we think the status is all about. But if you look closely, there's something else in this status message that's very unusual. It's that my local copy of the branch is over 100,000 commits behind my remote copy. Remember how the repo is moving really fast? This is about 2.5 weeks of activity. So I go on vacation, come back, run git status. Oh, I'm going to wait a while because I'm so far behind. This was not terribly unusual. And so we said, let's find out what's going on. Let's make sure that that's actually the part that's going on. So we started using a tool called Perfew, which does performance traces. So I'm going to have a few of these up on my slides. You can see there's a stack trace with method names, and it shows the % of CPU time spent in that method and the absolute time. So we see that it's actually handling this alias URL thing, which is actually outputting that line. So we were saying, yes, that's definitely it. Let's drill in a little more. We drill in really far down into that Perfew, and we find out there's this method called paint down to common. It's very important to the merge-based calculation for Git. We see that that's taking 65% of the time. If you dig in more, you see parse commit is taking almost 60%. This one method is taking a long time. So let's say maybe there's a way that we can improve that parse commit method and make it faster. But parse commit seems like it's a very well-tracked method in the Git code base, so that might take a while. So instead of doing something hard, let's do something easy first. The first thing to do is let's get our users unblocked. If they're in this mode where they're very far behind their remote branch, maybe they don't actually need that exact number of 100,000 whatever. They just need to know that they're different. So let's tell them, hey, it took you a while to run this computation. Maybe you should use this new flag called no ahead behind, and it won't take so long. And so if you say, oh, I saw that message, next time I run it, I put in that flag, hey, look, it took 2.1 seconds. That's much better. That's definitely in our realm of this is usable. A lot better than the 18 seconds from the previous command. But users aren't going to want to call this every time. It's an extra keystrokes to type. So we also gave them an opportunity to use a config setting. Hey, if I set status ahead behind false, just run git status, and it doesn't do that. I can always override it by saying ahead behind, and it will actually give me the right number. But for now, we can get them such that they very quickly do this. And we were able to watch the telemetry and see that there's a lot of adoption to this. So we were seeing a lot of people saying, hey, this is taking a while. Let's start using this. Notice that it's saying they refer to different commits. Right? It's just that amount of information, and that's enough for most users. The one thing I want to mention is that you might be thinking, hey, the Windows repo is just incredibly large. Why should I care? This isn't going to help me. Well, it's not just the Windows repo, especially when you're talking about parsing commits to do a graph traversal. A lot of talks about graphs in this session. I've been really happy about that. So for instance, if you do git log graph on the Linux repo, on my Linux virtual machine, it took over 7 seconds. That's too long. To show 20 commits, it took 7.7 seconds. And that's because it's walking the entire commit graph before it outputs a single commit. So this is something where, yes, real repos that normal people use that are not in this giant, enormous repo, they do have these types of issues. So I want to talk now for 3 slides that are going to get super technical. And I hope if you bear with me, I'll get back to these nice pictures of command lines that everybody loves. So what's happening with the commit walk logic is that it's going to call this method called parse commit gently. And what it does is it passes a struct commit that essentially contains an object ID and says, please fill in this struct commit with some extra information. And that information is going to be, I'll get to that in a little bit, but it passes that struct commit down to the object database. Those are your pack files and your loose objects. It searches through those to see, hey, do I know that object? Yeah, I found it. And then the object database returns a buffer. It has to decompress that buffer, and then the parse commit gently has to parse it. And it's essentially a plain text parse to pull out this data. And then it returns the struct commit filled in with some additional information. It's got the parents for that commit, so you can walk to its parents. It has the root tree, so you can find the tree from that commit. It also includes the commit date, which is very helpful when you're doing certain date order things. So this method is pulling all this information out, and it's doing all this parsing. Well, maybe if we just said, let's not do this plain text parsing and decompression, let's just get exactly this information that we need, and let's store it in a specialized file. So that's why we built the serialized Git commit graph. This is a very special file, and it's got just 4 basic parts. First thing is it's going to be a sorted list of commit IDs. It's got a little fan-out table to help search go a little bit faster, but you can binary search into this to say, do I know of this commit? Hey, I found it. It's in this row of the table. Then you can move to where all that extra data is. Just follow that row over to the next table, and you can get the tree ID, you can get the date, and you can get a couple parents out. I'm going to refer to these parents using not their object IDs, but just an integer to say, hey, if it's in the graph, look at this row. So it's a lot cheaper. It's only 4 bytes instead of 20. But you might be thinking, hey, what about octopus merges? There's more than 2 parents in an octopus merge. Well, that's why the second parent could also point into a table of edges for octopus merges. That's probably going to be very small. There's not too many octopus merges out in the wild, but it does permit that. So you can just go to this file and very quickly navigate into the file and then pull out this information, and then you can bring it back. And at no point do you have to do any decompression with zlib or something. So now we can modify this parse commit gently, and one additional thing we're going to return is a graph position in my struct commit. And that's going to be very important in a little bit. So now when I get my struct commit to parse commit gently, it's not going to go to the object database. It's going to go to the commit graph. If this struct commit doesn't have a valid graph position, we're going to do binary search into that object list and say, hey, do I find it in the graph? Great, let's pull that data out. And since the parents were referred to by graph position, well, those parents are going to have their graph position when they get called to parse, and they can navigate immediately to their position of the data. So you can do an O1 lookup. So instead of having something n log n, it becomes order n overall. And again, we have a fallback. If it's not in this graph file, let's just go back to the object database, just the same as normal. And everything's going to work out just fine. It's going to be just as slow as it was before, but it'll work out. All right, are you still with me? All right. Now you can get back to this command line pictures that you all wanted. So before, when you did this git log graph on the Linux repo, it took 7.7 seconds to get these 20 commits. And then now, it takes 1.3. Because of all that parse time it was spending checking in these commits and unzipping them and parsing them as plain text, it now goes straight into that structure, pulls out that data, and it can move on really fast. So that's a pretty big speed up on a realistic data set. So let's take a look at our Git status. And I'm telling you that I'm taking screenshots, and I'm seeing a lot of variance in these numbers, so, but that's just how it is sometimes. When I run status now, and I say, just to make sure I do the head behind, before the graph, in this time, it took 26 seconds. 23.6 of that was walking the graph. But as soon as I put in this graph, and I say, please use the graph, it's going to take 8.8 seconds. Again, that's a big jump. And that's going to be helping our users a lot. The important thing about when you say you have a performance gain is to not just give up as soon as you have a gain. You're just like, let's go back and rerun our performance tracing, and let's see what else we can do. What else can we improve? And I pulled these screenshots from my purview trace, and I put them in this slide, and I said, wait a minute, this doesn't look right. I looked at this left-hand column, and I saw these 3 instances of mark parents uninteresting calling has object file. The whole point of this graph was to avoid looking at the object database. Why are we calling this method has object file? It's going to go to the pack files and loose objects. Turns out, in the merge code, paint down to common, it calls something that does this, but it's not in the git log code. So it doesn't hit that pace. So when you're looking at the git log as your performance measurement, it doesn't happen. But it does happen here. Nice thing is, though, it's a 1-line fix that's already on the mailing list and in version to master. And with that 1-line fix, we go from 8.8 to 5.1 seconds. There we are back at our typical case, even with walking these 100,000 commits. So thanks very much for the community for all these comments on those sorts of things. On the right-hand side, I do want to point out that there's another thing that I was expecting to see, because I saw it in an earlier perfect trace, especially with the git log, is that you see I'm parsing the commits in the graph. You can see, oh yes, there is some time being spent parsing the commits in the graph, which makes sense. It can't go to 0. But there's a thing where I'm filling the commit where there's this insert parents or die, which is me looking at the parents and making sure I load them up. But there's this other method in there that's taking 6.7% of lookup tree. Right? I told you that the struct commit needs to have its root tree. But what does a root tree have to do with computing merge bases, or how far behind I am? We're loading these trees for no reason. So we're looking into it. We haven't figured out exactly how to do it cleanly. We're looking into making those tree lookups be lazy, so you only look them up when you really need a tree. And that way all of our commit walks can stop looking up trees, because again, we looked at 100,000 trees that we never ever needed. So we got that on the backlog to do very soon. That'll give us more improvement. Looking to the future, this git log graph is my favorite command, right? So I love looking at these pictures of graphs. And here on the left, we have the command line, what it looks like for the Windows repo. And here on the right is what it looks like to do a file path graph history on VSTS. So you can show the graph over there. On the left, the command line was taking 9.3 seconds, and this is after the graph, the serialized git commit graph I was talking about. This is with the improvements. But on the right, it took 391 milliseconds. And that includes a round trip to the server. So what I can tell you, because I worked on this feature, is that there are ways that we can make the command line run as fast as that. We just need to get there. And the serialized git commit graph is step one. And we're going to continue working on that and continue working on that until it's faster. And I also want to point out that, again, remember the git log on graph for the Linux repository. If you can do it on a kernel folder, for instance. It's 1.8 seconds. We can still get that down low, too. So this is like my shining beacon of where I want to be. I want to get these git log graph commands to be super fast, immediate for users. They're not waiting around to have it, because this is so useful. We can see when merges happen. You can see which commits are independent, and that's very helpful to me and hopefully to you. So I want to thank you all for listening to all of us talk about this. And if you want to hear more about how we're doing performance improvements on Git or how the Windows repository transitioned, there's some things to read on the internet. And also you can hear Johannes talk with Ed a little bit more on the All Things Git podcast about how Git for Windows came to be. And before I go, I do want to say this has been a great conference. I want to thank our organizers for putting together such a great list of talks. So let's thank them.